Thank you. Okay, I'm Eyal Gruss. I'm a machine learning researcher and a freelancer. Please speak to me if I can help you with your optimization problems. I'm an artist working with code, media, and text, and I teach computational creativity at the Holon Institute of Technology. I want to speak today about combinatorial optimization, and these are problems where we need to find solutions based on selections, matching, assignment, arrangement, for example. In these problems, we have discrete variables, or variables which can be approximated as discrete. We have constraints, which may be complex, nonlinear, global, and we want to find solutions that satisfy these constraints. We may also have an objective function or several to maximize or minimize. And we have many, many combinations as possible solutions, too many to go to enumerate them all. So some common types and examples for combinatorial optimization problems. We will mostly speak about the general domain of constraint satisfaction. The canonical problem here is when you have a Boolean proposition and you want to check if it's satisfiable or not. In the puzzles domain or recreational math, we can think about solving crosswords or Sudoku. We have crypto arithmetics, so you have some cipher, you need to find a mapping between letters and numbers. The 8 queens problem, for example, you want to put 8 queens on a chessboard so that no queen attacks any other queen. But we can also talk about more real-world problems, so resolving software dependencies, for example, when you do conda install, automatic type inference, and most importantly, arranging wedding seating, where some people must sit together and some people must sit far apart. And also, let's discuss some more domain-specific problems. So we can talk about packing or the dual domain of covering, where we have some resources or assets and we want to allocate them to different bins. Scheduling is a very real-world problem. You may have employees you want to assign into shifts. You may have a manufacturing floor with machines and tasks and some order for these tasks. This is called job shop sometimes. And school timetabling is very difficult. So you have classes, rooms, subjects, teachers, hours, a budget, and you need to make everything work together. Lastly, you can discuss routing or network flow problems. And probably for these, you can use the methods we discussed today. Probably you would like to use a dedicated solver. The canonical example here is traveling salesperson. You want to go through all cities in the shortest path. I want to talk today about ORTools. This is Google's open source software suite for operations research. Probably the most popular open source one for these kinds of problems. And the support is amazing. So they deal with issues like the same day. It's a small team from France. And it's also very good and very fast. So the solver we will talk about today, it started in 2018. And from that day on, it virtually won every category each year in the MiniZync combinatorial optimization challenge. And we will speak about the CP-SAT solver. CP stands for constraint programming, and SAT for satisfiability. So in CP-SAT, what happens is it's based on order encoding. It reformulates a problem as a problem in logic. So if you have an integer variable, say I, which can be either 1, 2, or 3, it will be transformed into a Boolean, into a few Boolean variables. So is I equal to 1? False or true? Is I equal to 2? Is I equal to 3? And also, so we can check ordering, is I less or equal to 2? Is I less or equal to 3? And it turns out that this is enough to have a Boolean representation that can capture also the order of the possible integer values. And you don't need to worry about this because this is done automatically and also lazily, so it's efficient. Why use CPSAT? So before I found out about how to CPSAT, I would either do heuristic optimization. So it could be very fun to think about, but unfortunately it doesn't assure you that you can get all solutions or you get the best solutions for your objective. And also, sometimes you don't know if you got the best ones or if you got them all. As I grow older and my OCD gets worse, I'm more and more worried about finding all solutions and the best solutions. So I need to do some kind of exhaustive search, and to make it work, I need to handcraft into this different optimizations. Optimizations which are different per each domain, hard to craft and error-prone, makes the code more verbose, and also the code itself is more error-prone, and in the end, it's usually not fast enough. And CPSAT can solve all of these problems. So, and this is a very simplified description, but it exhausts the search space by methods like branch and bound, branch and cut. Essentially, what they do is that they are able to prove mathematically that large areas of the search space may be eliminated and thus save a lot of time. So you get assurances that you get the best solutions or all of the solutions. It's a generic method, so you need less handcrafting, you get simpler code, and for me, I've seen like 1 or 2 orders of magnitude speed up. But you need to accept a different programming paradigm, which may be new to some of us. It's declarative, so it's not functional, it's not imperative, it's declarative. It can be more strict and can be more, have a more verbose formulation. And of course, you still need expertise to do the modeling. But I hope to convince you today that it's worthwhile to look into this and maybe try it for your next optimization problem. So we will see most of these usage patterns today, but essentially different questions that you can ask is like find a solution or find whether a solution exists. Is it a problem, the solution feasible? Finding all solutions. Sometimes it's not possible because there are too many. You may have an objective that you want to maximize or minimize, so find a solution optimizing the objective and find the objective value being optimized. And then you may want to find all solutions optimizing an objective. The way that we will see today, the way it's done in all tools is first find the optimal solution, find the value, constrain this value in your problem, and then find all solutions. And by the way, multi-objective works in a similar fashion. You may want to remember that you can also do it sometimes in Python. If there are not too many solutions, sometimes it makes more sense to just get them all and do the optimizing and pre-processing and filtering in Python for the objective that you didn't put into the initial problem. I want to show today a problem that I think is beautiful. It's non-textbook. I consider it real world. I'm not sure if you would. It's non-trivial. And it will show us how to use O2 CPSAT and some modeling principles and the general approach for the solution. So this question was posed by Philip Cohen and Ross Eckler in 1979 in the journal Wordways as a challenge. Can any form, like a diamond or a pyramid, contain all 26 letters? So originally this was about English, and the question was, can we make some geometric form, put in all the letters that sit nicely one next to another in some 2D or 3D geometry, but also form words or form text? And let's solve this today, but using 27 letters with Hebrew. So it will be a 3D perfect pentagram. Something like this. So Hebrew has 22 letters. If we add the 5 final forms, אותיות כמנפץ, we have 27 letters total. A perfect pangram this is like a word game, a word play. It's text where each letter appears exactly once. This is the idea. Let's put the letters, the 27 letters, into a 3 by 3 by 3 cube to form 27 words, and we will have 9 words in the x direction, 9 words in the y direction, and 9 words in the z direction. So 27 words. Now, it is mathematically impossible to have all the final and non-final letter forms in the correct place, so we need to relax this, and we will allow interchanging, like the final form, like mem regila mem sofit. We won't care where it sits in the word. So this, we have to accept this. So analysis of the plans provided by Princess Leia shows us the cube, which can be dissected into 27 subcubes or cells. We could put one Hebrew letter in each of them. And of course, the challenge is to rearrange, find the order for these letters so we get 27 words. Now, this is a hard combinatorial problem. We have a combinatorial explosion. For example, if we look at letter permutations, 27 factorial, you can divide by the symmetry of the letters of the final forms if you care about that, and you get 10 to the 26. Alternatively, we can look at word permutations. So we will need about 2,000 words, and if we choose 9 with older permutations, we get an even larger number of 10 to the 29. Either way, exhausting the search space is intractable. It will take us more time than the age of the universe. So we need another method. By the way, this doesn't take into account the symmetries of the cube, but it's interesting to discuss. So symmetries are bad because they mean redundant solutions. Even if I fix, and of course this is very domain specific. So in our case, even if we choose, sorry for this, a left-handed axis system starting from this certain cell, we still have some symmetry left. I can do these 3D rotations, and these solutions are redundant. So if we take the 3 words, Eyal ata ashaf, Eyal, you are a wizard, we can get the same solutions by just doing these 3D rotations. And we don't want this. We want to do symmetry breaking. We want to eliminate redundant solutions. And there are different ways to do it. It's very domain specific. We need to think about it. It can put in errors. Here is one example. So we can choose a specific letter. Maybe we can choose the letter in a smart way. In this case, I think hey is the best one. And then we can break part of the symmetry by constraining the location of this specific letter to 10 of the 27 places. Specifically, only the 10 places that form unique combination of indices. But let's try a simpler method for this talk. So let's go into code. The problem representation, I suggest using 27 integer variables for the cells, and the values for each cell would be the Unicode value of the letter. Now, mind you, a lot of problems can also have a dual representation. Instead of having variables for the cells and values for the letters, we could have variables for the letters and values for the cells. Sometimes it's more efficient or more simple to do one or the other. If you have graphs, you can look at either nodes or edges. But essentially, the way to add variables in OTool CPSAT is model.newIntVar and some range. And here I'm just giving it these Python references, either as a flat list or as a dictionary into a cells dictionary indexed by the location. This will be helpful in the following constraints. Also, I need 27 times 22 booleans, and these would indicate for each cell if it does contain the specific letter, true or false. And this similarly is added by model.newBoolVar. Now these represent the same. We need to tie them together with if and only if constraints. This is our first constraints we're seeing here. This is called channeling. So I'm adding a constraint that if the variable in my flat list has the value of a specific letter. This happens only if, so it's implied by the Boolean, if the Boolean contains that letter in that specific location, and vice versa. If the Boolean does not contain, then the flat list cannot have that specific value. And this may look like overly verbose to you, but actually this is the way things work anyway behind the scenes, and this will prove to be very useful and allow us to model the constraints. So let's go into the main constraints. We want each letter to appear exactly once, except the final forms, okay, they appear 2 times. So we can sum over these Booleans, and the sum should be the allowed count, either 1 or 2. So in the model.add, I put in the Python, the sum, and the equal. This is like declarative programming. We want all 27 words to exist in our vocabulary. And also, so my vocabulary is like all the inflections from H-spell dictionary, which I intersected with MC4 from Common Crawl to get like popularity scores for the words in the corpus. So let me put here the scores. We will use them later for the optimization. The scores are just integer variables with score values in some range. And the global constraint, add allowed assignment. So for the first cell in the row, second, third, and the accompanying score, they have to be one of the allowed options in my list of allowed words and their scores that I have. Additionally, let's have the middle word be our sweetheart's name. So I'm celebrating 2 years today with my girlfriend, and for the sake of love, also for symmetry breaking and faster computation, let's put the letter in cell 011 yod, in 111 ayin, and in 211 lamed. And finally, we have the objective, and we can solve. So I suggest taking the maximizing the popularity score of the least popular word used. So I want the rarest word that I need to use to be as popular as possible, so it won't be too strange. I define a new variable, an integer called worst. It takes the value of one of the scores, and I do the add mean equality. So worst will be constrained to be the minimal value of scores. And then I add the objective, maximize worst. And then I can do solver solve for my model. After I find this optimum, if I want to find all optimal solutions, I need to clear the objective with model clear objective and add it back as a constraint. So I could now constrain worst to be equal to the optimum value I found. I change the solution mode to enumerate all solutions, and I solved. Again, just adding a callback for collecting the solutions. And we have a Colab. If you don't know what a Colab is, it's a Jupyter notebook run on Google Cloud. You can play with this later. It takes less than 15 minutes to run, and you will be able to put in your own loved one's name and get, if you find a solution, you can get a URL with this solution. So let's look into that. So I did run it before because it takes 15 minutes and I have less of that time left. We can go a bit into more detail. We've seen the essential commands before. I install our tools. On Colab, it's actually already installed. I download this word list. I have a different repo, Hebrew word list. So let's take one of the word lists from there. And then I have some Python to do like loading it and fixing, pre-processing the final letters. Let's see how it looks like, and splitting the score in the word. So the top ones, the most popular ones, are these short prepositions. And the last one, the most rare ones, are these inflected feminine third forms verbs, which appear in the corpus only once in this case. Next, I want to filter the word list to only allow words with 3 letters. And I want these letters to be either unique Or if I have one of those with the final forms, okay, they can appear twice. So let's do this filtering in Python. And again, let's see what we get. So the most popular ones are like he, she, I, but. And the rarest ones, there are some I'm not sure what do they mean. But okay. Also, I limited to be faster the length of the list I will use from, say, 2700 to 2000. If the limit is high enough, then like a higher number will give us a faster solution for the first solution, but a lower number can give us a faster solution if we want to find the optimum or all solutions. Okay, let's go into ORTools. I import ORTools. I define a model. I define a solver. And if you want to look into logging, you can see how it's done later here. Creating the variables. So this is the 27 integers we've seen before, 3 by 3 by 3, with a new int var, saved both as a cell with the position as a tuple in a dictionary, and a flat list, just easier. The references to the variables of the model, it will be easier to use them. We had the booleans and the channeling. So you remember, we had like 27, these are the cells, by 22, these are the letters. I create the booleans, and I add these channeling constraints with the, so it's if and only if. If the boolean is true, I want them to be equal. If the boolean is not true, I want them to be not equal. Why am I doing this? Because now I can add these count constraints. So if it's one of Kemena pets, it needs to appear exactly twice in the cube. And otherwise, I could put a 1 here, but you can also write add exactly 1. So over the booleans, other letters can appear only once. Remember the sweetheart option. So the code looks long because I added an interface and some checks, and maybe add it to the vocabulary if it's missing. But essentially, it's only these constraints. So I want the first character in this specific cell I chose. The second one gets, in my case, the yod, the ayin, and the lamed. So we will have Yael as the middle word. And finally, we need to make sure all assignments are allowed. So I just get the Unicode values for the letters of the words and the score. I put it into an array of a list of lists. Let's see the 5 first. So it's like the value of the first letter, the second letter, third letter, and the score. This is just a helper function to get the score variable. But the interesting thing is these add allowed assignments. So again, in some row, the first cell, the second, the third, and the accompanying score should be only one of the list, one of the options in my allowed list. Okay, now we can solve. So if we want just to check feasibility, this takes about 1 minute. We can do solver.solve model, print the status. Actually, it should read feasible, but they mean feasible by optimal. We're not doing optimization, but this is the way it prints out. But now let's say we want to find the optimal solution. So you remember maximizing the minimum popularity score, some callback for the logging, and the same commands we've seen before. Define the worst variable as an integer, add min equality, so worst would be the minimum score, and maximize that. This is my objective, and solve with some callback. And this takes about 8-9 minutes, and you can see the objective gets better. And in the end, the rarest word I must use is tsaban, like their turtle in feminine form. So maybe we can think about a more interesting or better objective, but for now it will suffice. And if I want to find all solutions, I have a very lengthy callback here just to collect solutions. I don't need to go over it. It just decodes and records the solution. But the important part we've seen before is clearing the objective. This is needed. Actually, I asked them to add this function, and they added it like one day after. I need to fix the constraint, so the worst would be equal to the optimum find before. And if I just want to find all solutions without a constraint, you can comment this out. Change the mode to enumerate all solutions. And define a collector and solve. This takes about 3 minutes. And you can see I found 2 solutions. If they are symmetric or not depends if you care or not about word order. And we can visualize, and we get a link, and you can do this later for your own choice of name. You can see the middle word is indeed Yael. Let's stare at this for a few seconds. And all words, like maybe not the best words, but all like 27 words in rows, in all 3 directions, we get real words in Hebrew. And sometimes you can even get like phrases if you really want to. Yeah, and you can try this later at this short link. So if you're interested, there's some information. Let me just mention what it is. You can look at it later. Some important references for all tools, CPSAT. Of course, there are alternative solvers in Python also. These are like the most popular in open source. I tried some of them. All tools was faster, but you can look into this. You're interested. More generally, there are modeling languages and wrappers in Python. Minizinc is the one used. It's not Python, but it has bindings. It's the one used in the Minizinc challenge. Also has an online playground. And other interesting options. Pyomo is like the rising star. And CPMPy allows you to work with NumPy arrays. And the other ones are just for linear programming and mixed integer programming, which is a subset of the problems we are talking about. And if you are interested in the more specific domains, scheduling, routing, NetFlow, like in the real-world problems, there are dedicated solvers with some offering by Google or AllTools and some other things to look into. And finally, some interesting research frontiers. This is from the guys from the CPMPy wrapper. They have PyCona trying to do automatic constraint acquisition, so deduce the constraints from positive or negative examples. And they also have another library working on interpretability and explainability. And if you cannot find a good solution, you want to know why and maybe how to fix it. For example, you have a schedule. It doesn't work. You want to relax something, so you get a good solution. And this is the LLM track. So, of course, you have some LLM stuff, trying to use LLM to build the constraints or to reason with the constraints. But it's like really initial stage, so I don't have something specific to recommend. Thank you very much.